The video you are about to watch is to be used as a supplemental tool only, and in no way does it replace or substitute class lecture.
This is a tutorial video on logarithms for grade 12 mathematics. This lecture explains the basic principles of logarithms as well as some working examples. Logarithms allow us to manipulate and interpret large numbers, especially when we plot variables graphically. Let us start with the definition of a logarithmic function. We start with writing down any exponential function as follows. Say y is equal to a to the power of t, where t is defined as the independent variable, y is defined as the dependent variable. Remember that a is defined as the base, t is the exponent, and y is the result of the calculation. We can also say that the variable y is a function of the variable t given by this equation. This brings us to the next step in the definition of a logarithmic function. Let us now write an exponential function as follows. X is equal to a to the power of y. From this equation, we define the logarithmic function as follows. Y is equal to the logarithm of x to the base of a. So y is the logarithm of x to the base of a, where we define x as the independent variable and y as the dependent variable. Thus, we say that the logarithm of x to the base of a gives us the value of y. In other words, to what power must a be raised to give the value of x? In other words, a must be raised to the power of y, and that will give us the value of x. From this equation, we can state the following. For a logarithm to be defined, the following conditions must be adhered to. The base a must be positive and real and not equal to 1, and x must be a positive number. Only then will a logarithm be valid. To summarize, this is a very crucial statement and it forms the basis of all logarithms. We start with an exponential function. We say that x is equal to a to the power of y. In other words, a is the base, y is the exponent, and x is the result. From this, we define a logarithm as y is equal to the logarithm of x to the base of a. And in other words, to what power must a be raised to give the value of x? That is the fundamental definition of a logarithm. This brings us to logarithmic identities. The first one we have is what we call the product identity of a logarithm. The product identity of a logarithm is stated as follows. A logarithm of x times y to the base of a is equal to the logarithm of x to the base of a plus the logarithm of y to the base of a. That is our first identity. We call that the product identity. Now, we need to set about to prove this identity. Let's just write the identity down again. We say the logarithm of x times y to the base of a is equal to the logarithm of x to the base of a plus the logarithm of y to the base of a. To prove, we need to prove this identity. We prove this identity as follows. We say let variable p be equal to the logarithm of x to the base of a and variable q be equal to the logarithm of y to the base of a. Then from the definition of a logarithm, which we explained in previous detail in the previous discussion, we can say that x is equal to a to the power of p and y is equal to a to the power of q. Let us now multiply x and y together. We say that x multiplied by y is then obviously a to the power of p multiplied by a to the power of q. Using my exponent rules, I can write this as a to the power of p plus q. Now again, apply the definition of a logarithm to this equation. In other words, the logarithm of x times y to the base of this a is equal to p plus q. But we define p as the logarithm of x to the base of a, and we define q as the logarithm of y to the base of a. So that is then equal to the logarithm of x to the base of a plus the logarithm of y to the base of a. And we have proven the first identity. The second identity is the quotient identity. The quotient identity and the quotient identity states that the logarithm of x divided by y to the base of a is equal to the logarithm of x to the base of a minus the logarithm of y to the base of a. We again need to prove this identity. It's quite important for us to prove it. Again, let p be equal to the logarithm of x to the base of a and q be equal to the logarithm of y to the base of a. Then again, from the definition of logarithms, which we use quite a lot now, we can say that x is equal to a to the power of p and y is equal to a to the power of q. Now, if we say x divided by y is then obviously equal to a to the power of p divided by a to the power of q. Using my exponential laws again, this is obviously a to the power of p minus q. Okay, now I can again apply the identity of a logarithm to this equation, and that therefore this means that the logarithm of x divided by y to the base of a is equal to p minus q. Okay, we just need some more space here. And thus, our next step then is to say that the logarithm of x divided by y to the base of a is equal to the logarithm of x to the base of a minus the logarithm of y to the base of a. The third identity that we need to deal with is the power identity. Now, the power identity states that the logarithm of x to the base of a and x to the power of n is equal to n times the logarithm of x to the base of a. Let us again prove this identity. We can prove this identity by stating that by letting p be equal to the logarithm of x to the base of a. Now again, using the identification of a logarithm, or the basic definition of a logarithm, this equation can be written as x is equal to a to the power of p. Now, let us now raise x to the power of n on the left side of the equation. Basic simple mathematical equation states if I raise x to the power of n on the left side of the equation, I must do the same to the right hand side of the equation, which means then that I can write x to the power of n is equal to a to the power of n times p. Then, from the definition of logarithms, I can write this as, that means, from the definition of logarithms, I can write this that the logarithm of x to the power of n to the base of a is equal to n times p. But we defined, when we started this proof, we defined it p to be equal to the logarithm of x to the base of a. That means the logarithm of x to the power of n to the base of a is equal to n times the logarithm of x to the base of a, and we have proven the power identity. The next identity we need to deal with is the root identity. The root identity, which is very similar to the power identity. The root identity states the logarithm of the nth root of x to the base of a is equal to the logarithm of x to the base of a divided by n. This proof is similar to the proof of the power identity, simply because we can write the logarithm of the nth root of x to the base of a be equal to the logarithm of x to the power of 1 over n to the base of a. And if I then apply the power law, power identity to this equation, I can say this is the logarithm of x to the base of a divided by n, and thus we have proven the identity, the root identity. Now that we have proven all our identities, we need an important issue with logarithms, and it might be necessarily in some applications to change the base of the logarithm. So let us state the change of base. If the change of base states that if I have the logarithm of x to the base of a, I can write that as the logarithm of x to the base of b divided by the logarithm of a to the base of b. So what I have done here in summary is I've started off with a base of a, and I've changed that to a base of b in this format. The issue is now we need to prove this. We just cannot accept this. It's quite important for us to prove this change of base algorithm. So again, let the log of x to the base of a be equal to p. And again, to this, let us apply the definition of a logarithm to this statement. Thus, we can say that x is equal to a to the power of p. Take the logarithm on both sides of this equation to the base of b. In other words, if I write this equation, the logarithm of x to the base of b is equal to the logarithm of a to the power of p to the base of b. I am allowed to do this because in the equation, what I do on the left-hand side of the equation, if I do the same on the right-hand side of the equation is still valid and still true as originally defined. Using the power identity, we can then say that p times the log of a to the base of b is equal to the log of x to the base of b. Then this implies that p is equal to the log of x to the base of b divided by the log of a to the base of b. But we defined p in the beginning of our proof as the log of x to the base of a. In other words, this is also equal to the log of x to the base of a. So we have proven that the log of x to the base of a is equal to the log of x to the base of b divided by the log of a to the base of b. That is quite a powerful tool we can use to solve problems. There are some commonly used bases. That we deal with in logarithm. The first one is the base of 10. The base of 10 is a very popular one. It's used in manual calculations are easy in the decimal number system if we use the base of 10. We also have the natural logarithm where we use the irrational mathematical constant e, which is approximately equal to 2.71828. And then we also use another base that is very popular is the number 2, which is used in computer science where the binary system is a fundamental application. There are two very interesting phenomena, I would say, that we need to discuss on logarithms. if we start with an equation, if we state that a is equal to a to the power of y, this can only be true if y is equal to 1. Only true if y is equal to 1. That is just logical. A to the power of 1 can only be a to the power of 1 being equal to a to the power of y can only be true if y is equal to 1. If I take the logarithm of this equation, I can then say that y is equal to the logarithm of a to the base of a, and this implies this initial equation can only be true if y is equal to 1, and that means that the logarithm of any number to the base of the same number is equal to 1. That is just something to be remembered and understood when we solve some problem. We say let 10 to the power of log a to the base of 10 be equal to x. We define x to be this. Therefore, we can say that the log of 10, the log of x rather, to the base of 10, in other words, we take the log of x to the base of 10, is equal to that value, the log of a to the base of 10. This implies this can only be true if x is equal to a. Right. Therefore, we can state from this proof that 10 to the power of log of a to the base of 10 is always equal to a. So if my base and my exponent in this equation is the same, then the value of this result, as proven using the basic definition of logarithms, is equal to the value of a. Okay, let us now get to some examples. If I start with example 1, if I start with the logarithm of 1,000, I can write that as the logarithm of 10 to the power of 3, because 10 to the power of 3 is equal to 1,000. If I apply the power identity, I say this is 3 times the logarithm of 10, and we've just stated that the logarithm of 10 to the base of 10 is always 1, so that is equal to 3. So the logarithm of 1,000 is equal to 3. So we've used the logarithmic identities to easily manipulate a large number. Logarithms can easily be simplified by application of the identities. If I start with 2 log 5 minus log of the third root of 64 plus 4 log 2. Now if I apply the identities correctly, I can easily solve this value. If I apply the power law, first of all, I say then this is equal to the log of 5 squared minus the log of 64, the third root of 64. I can apply the power law to this part of the problem, and that is 2 to the power of 4. Now I know from the product identity that log 5 to the squared plus log 2 plus the log of 2 to the power of 4, I can write that as 5 to the squared times 2 to the 4. If I apply the quotient identity to this part of the problem, this becomes divided by the third root of 64. And if I solve this problem, which I can easily do, if this is equal to the log of 25 times 16 divided by 4, and this will give me an answer of log of 100. Now the log of 100 is the same as the log of 10 squared, and that is equal to 2 log of 10, and we know the log of 10 to the base of 10 is 1, so the answer of this problem is 2. So by just applying the identities of logarithms, we can easily solve a problem like that. Okay, let's move on to an examination example that I found on one of the old examination papers. What the examiner said is the price P of each item of a consignment of items is given by P is equal to the log of 10 plus Q over 2, where Q is the number of items supplied at a price P in rands. Then the examiner asked us to calculate P and the total price of the consignment when the consignment has 1980 items. And in the second part of the exam paper, he asked us for the number of items in the consignment when the price of each item is 2 rand. Now, let us start by answering the question as follows. We've been given that P is equal to the log of 10 plus. Now, in the first part of the exam question, the examiner said the number of items is 1980. So we replace Q by 1980 divided by 2. And then this is obviously equal to the log of 10 plus 990. And this is obviously equal to the log of 1000, which is equal to the log of 10 to the 3. Then if we use the power identification of the logarithm, that will allow us to say that P is equal to 3 times the log of 10. Now the log of 10 to the base of 10, as we proved previously, is equal to 1. So P is equal to 3. That means each item in the consignment costs 3 rand. And we have 1980 items. That means the total price will then be 3 rand. The total price is equal to 3 rand multiplied by 1980, and this is equal to 5940 rands. Then thus we have now answered the first part of the question, and looking at the second part of the question. The second part of the question, just to remind us, is then determine the number of items in a consignment if the price of each item is 2 rand. We again start with the formula that the examiner has given us. He said the price of each item is the log of 10 plus the number of items divided by 2. We now have 2 rand for each item, so that means that 2 is equal to the log of 10 plus Q over 2. Now what we do now to solve the problem is we write this equation on the left hand side. We write 10 to the power of 2 is equal to 10 to the log of 10 plus Q over 2. In other words, everything over the log. This first, on the left hand side of the equation, then we have 100. And as we have proven previously, on the right hand side of the equation, 10 to the power of log of 10 plus Q over 2 to the base of 10 is just equal to 10 plus Q over 2. We have proven this previously. Now we need to solve this equation. Therefore, we can say that Q over 2 is equal to 90, and that means that Q is equal to 180. That means that the number of items will be 180 if the price for each item in the consignment is 2 rand. Thus, we have solved the exam problem, and I hope you understand algorithms better, and I hope you do well in the examination. Goodbye.